It has been established that a stable state of all substances, and not only of C60 buckyball, is the 60-particle stable cluster. Experimental results of Binnig and Rohrer are analyzed below, and it is found that the formations on a 7x7 reconstructed silicon surface are not individual silicon atoms, but are 60-atom silicon clusters. Scanning tunneling microscope (STM) revealed important information about the surface structure of the solids. The maxima observed on this reconstructed silicon 1-1-1 surface are interpreted as silicon atoms sitting on top of silicon 1-1-1 surface, quote-unquote, in distinct sites, and arranged in a unique manner. However, how could an atomically smooth surface of silicon 1-1-1, or the atoms, ensure the strict observation of a distance, equal in all cases, between neighboring maximums? A distance which is much greater than the diameter of the atoms. So, either the atoms from the surface of silicon 1-1-1 are not indistinguishable from one another, or the silicon atoms in some cases can have a diameter much greater than the known one. Both suppositions are evidently unacceptable. Maximums must comprise something else and not silicon atoms. Maximums must be some objects different from silicon atoms. Objects whose diameter is equal to the difference between neighboring maximums. One of the most attractive features of the scanning tunneling microscope STM is that with it the scale is measured directly and not through comparison as in scanning electron microscope SEM. Thus, the observer may judge for the real dimensions of the objects under examination and can draw direct conclusions from them. We will now take advantage of this exactness and will observe facts of far-reaching importance, which were not noticed by the authors. For this reason, make sure you observe where the long diagonal under discussion is situated, lying between the first and the second deep minimums. The 4 red dots indicate the 4 maximums lying along the long diagonal. Here the red dots are placed on the 12 maxima of a 7x7 unit cell. The 9 minima around them are also seen. As was mentioned, scanning tunneling microscope (STM) provides a unique possibility, unmatched by any other technique, to measure exactly the real size of entities of molecular and atomic dimensions. Thus, the authors have measured the long diagonal to be 46 ± 1 angstrom. It can be seen that the long diagonal passes through 4 maxima, which divided into the following 5 parts. 1 part, situated at its middle, whose length is equal to d sub exp. 2 parts, at its ends, comprising the distance between the deep minima and the maxima neighboring them, with one and the same length, equal to d sub exp. And 2 more parts, each one of which is of length equal to 2d sub exp times cosine of 30 degrees. From where we can calculate the value of the quantity d sub exp. As seen, the value of the quantity d sub exp is 7.12 ± 0.15 angstroms. To see how this value compares with the diameter of the silicon atom, divide the density of silicon by its atomic weight to obtain the number of moles of silicon in 1 cubic centimeter. The product of the obtained number of moles in 1 cubic centimeter and the Avogadro number gives the number of atoms in 1 cubic centimeter. The inverse of the obtained result is the volume occupied by one silicon atom, and the cubic root of that volume yields the diameter d sub si of the silicon atom. Obviously, the value of d sub exp is not the diameter of a silicon atom, calculated below from the known data. The value of d sub exp is of special significance. It comprises the experimental value of the diameter of the so-called stable silicon cluster. We can now compare the experimentally obtained value of the stable silicon cluster diameter with the theoretically predicted value of the thermodynamically stable silicon cluster diameter. It is the subject of another presentation where explanation is given as to why the theoretical value of the stable drop radius r sub 0 of the stable cluster should be equal to 1.45 times the diameter of the silicon atom. Radius r sub 0 of the thermodynamically stable cluster extends from the center of the cluster to the centers of the outmost surface particles making up the cluster. Next, we want to know how many silicon atoms fit into the silicon stable cluster. For this reason, we have to consider the radius r prime sub 0 of the sphere enveloping the outermost molecules of the cluster. As explained in another presentation, the particles within the cluster must be packed tight, and the only possibility for empty space is between the stable clusters forming the crystal. Here, we see an amazing result. Analysis of the data obtained by scanning tunneling microscope of the reconstructed silicon 111 surface reveals that the maxima observed are not silicon atoms sitting on that surface, as they have been interpreted, but are 60-atom silicon clusters, exactly as theoretically predicted when considering a modified Gibbs-Thomson isotherm. A stable 60-particle cluster is observed in another well-known study, the 60-carbon Buckmann-Stiefel. By using the data corresponding to a carbon atom and applying the same procedure as above, it is again obtained that a stable cluster, this time of carbon, consists of 60 carbon atoms, as the experiment confirms. It will be shown in another presentation that 60-particle thermodynamically stable drop is not only characteristic for silicon and carbon, but that any substance in its thermodynamically stable form is made up of thermodynamically stable clusters, drops, consisting of 60 atoms or molecules. This is supported by all the data for 175 substances, which are available in the literature. It was shown here that besides molecules giving rise to the molecular discontinuity of bodies, there exists also, so far unknown discontinuity, connected with the existence of a polymolecular particle, corresponding to the two branches of the specified Gibbs-Thomson isotherm. The established ultramicro discontinuity, corresponding to the thermodynamically stable polymolecular particles, is of special importance because it ensures the crystals in the bodies in general the lowest level of their free energy, respectively, the greatest thermodynamic stability. The theoretically predicted and established for the first time ultramicro discontinuity is a phenomenon which can have significant theoretical and practical importance, because the properties of the thermodynamically stable body, crystal, consisting of stable, ultramicroparticles, can be essentially different from the properties of a body with a less stable structure, a molecular discontinuity structure of the ordered crystal.